Good morning. My name is Wojciech Rosinski and I am the CTO of ReSpo.Vision. It's a great pleasure for me to speak at this event. I will present the topic on how to build a deep learning-based system for precise post estimation in sports in just 3 months. To outline the plan of the presentation, I will start with introducing the company, ReSpo.Vision, and myself. I will then talk about approaching system building, which is based on machine learning methods. Afterwards, a few ways on how can you improve the quality of predictions of your deep learning models. Then, I will talk about how we have set up pipeline in the case of ReSpo.Vision, where we have many modules interdependent of each other. And to sum up, a few general ways of speeding up the development process. How to quickly debug the models, how can you experiment quickly and efficiently, and how to deliver results faster. We at ReSpo.Vision are a deep tech company which aims to revolutionize sports analytics, starting with football. We are building an automated three-dimensional data acquisition and processing system, which is based on video broadcast feed. Those are 3 key qualities: automation, three-dimensional data extraction, and flexibility, which comes from processing the video broadcast feed itself. To achieve this goal, we employ state-of-the-art deep learning techniques and combine them with our custom-developed solutions, which make use of both the deep learning and classical computer vision methods. The environment that we have chosen for us comes with its unique set of challenges. There is only one camera view available, the conditions in which matches are played are diverse, and also the quality of the videos may vary greatly. So, we have to create a robust system which will be able to fare well in those diverse sets of conditions. To introduce myself, I am the CTO of ReSpo, so I am bridging the business side with the technology side. I also manage the machine learning development team and have some development responsibilities myself. I am responsible for setting up the infrastructure side and choosing the technology stack, also for creating the complete system architecture and a coherent pipeline which enables end-to-end processing. I also work on developing core deep learning models for classification, detection, and key points estimation. Previously, I was able to gain extensive experience in both research and development and engineering side of machine learning projects. Some of them employed deep learning models as the core of their solution, and many of them combined multiple models to achieve a coherent goal. I have some of those projects were done on universities, University of Warsaw, Warsaw University of Technology, some of them for commercial companies. So I combine university work and industry work. I'm also a Kaggle Master with 19 medals, 19 competition medals, 2 golds, 10 silvers, and 7 bronzes. I managed to gather them on a diverse set of competitions, some of them computer vision, some natural language processing, and some of them tabular data. 2 things that Kaggle taught me, which I employ in ReSpo, are hardcore model optimization techniques and ways to quickly and efficiently test different hypotheses. So, you want to build a system which will be based on machine learning. But how do you approach this? First, you need to understand the problem. What exactly would you like to achieve? Also, what will be the value coming from the solution that you are developing? You need to define input and output of the system. This will enable you to better understand the environment. So, what will be the system raw input? Are there any constraints that you can put on this input in order to better specify the requirements for the system? Also, what will the system return? What is the main goal to achieve? Next, you need to understand the input data. How diverse the environment in which you want to deploy your system may be. Are there any specific edge cases which you can identify? And can you think of different ways to solve them? Next, you should draft the architecture. Think about ways of breaking down the system into components and modules, and also define the relationships between the modules themselves. In our case, we are taking as input raw video, then we run it via end-to-end pipeline, and what we output is numerical data. To give a glimpse into the ReSpo.Vision system architecture, we start with those raw broadcast videos, which need to be filtered, as some of the frames we want to process and extract information from, and some can be simply ignored, as they will be close-ups or looking at the audience. At the top, we have pitch geometry pipeline, for which we have developed our custom solution based on deep learning model, which is then supported by lens distortion correction algorithm. And we also have an algorithm for estimation of the pitch panorama, where we combine the characteristic points extracted from the pitch with the pitch panorama. We are able to create a single view, three-dimensional ball trajectory model, so we can estimate the trajectory in three-dimensional space. Next are the key deep learning models: the player and ball detection model and the body key points model. The detection model is of the utmost importance, as its output will influence the quality of the others. For example, the key points model takes crops coming from the detection and processes them to improve the quality of the predictions. We also have a number of modules for extracting different player characteristics, such as teams, their numbers, and the visual representation in the form of an embedding. Also, we need to sequence the video and split it into coherent parts. For this, we have a separate module. After all this processing is done, the data can be then gathered and treated as an input to the tracking algorithm. The tracking algorithm uses different data sources to capture identities of the players in coherent sequences. This we can use for aggregation to further stabilize the output of the system. And the output of the system itself is twofold. First are the custom visualizations, which we can create by imposing the data extracted from the pipeline onto the raw video. Also, there is this detailed numerical data which we have acquired, which can then serve as an input to contextualization algorithms and ways and computation of advanced metrics. When we combine those features coming from the contextualization and statistics computation with this raw, detailed numerical data, we can use it for events and scores predictions. The environment that we have chosen comes with its own set of challenges. For deep learning models, the main challenge is the fact that the objects that we want to extract information from are very, very small. And if they are far away, their resolution will sometimes be as low as 10 or 20 pixels. It is very difficult to extract meaningful information from objects of such small sizes. The second aspect is that due to quick camera movement, the image may change dynamically. This will result in blur, and for those frames, we still want to be able to accurately extract the information. The challenges which are related to the key points is the fact that the objects that we want to predict key points on are very different from, let's say, this baseline key point estimation scenario, where the object which you would like to predict is usually based on the center of the image, and it is also a few dozens, hundreds pixel high. So the objects are usually much bigger than the ones for which we want to predict the key points. There are also occlusions happening, and if the players partially occlude one another, it may be very difficult to estimate correctly parts of the body which cannot be seen on the image. This can be changed if we switch from per frame estimation to estimation on sequences, where we can also integrate the temporal aspect. Then come challenges related to the geometry transformations. Those are related to first, the video feed being just from single camera at a time, so we are not able to use the industry standard methods which combine information from different perspectives for prediction. The second main challenge is the fact that the camera parameters are unknown, so we have to estimate them during the mesh itself. As far as tracking is considered, we have broken down the algorithm into local and global parts. The local enables us to track players in a coherent sequence, and the global then combines information from all those sequences into global identities. In tracking, the main challenge is the fact that there will be many situations where it will be difficult to identify player characteristic features, such as their numbers or characteristic visual features such as shoes or their body color. But there are some ways with which we can improve the quality of predictions of our deep learning models. The first such way is pseudo-labeling, where we employ our model to predict different instances, and then we integrate those predictions into the training data set, and we retrain on a mixed data set, which is a mix of those pseudo-labeling labels with the human verified ones. Second way is to tune the parameters of the model and the architecture itself to topic-specific challenges. One of those challenges is the accurate detection of small objects. So we can tune our architecture to concentrate specifically on this challenge. And we have done so via aggregation of information from different levels, layers of the model. So we are using multi-level features to more accurately estimate the small objects poses and masks. We also want to maximize training and prediction input resolution where possible. This comes at a computational cost, so we have to consider an optimum between model quality and model speed. There are also some smart data processing methods which you can employ. We do so in order to bring input sample distribution closer to the model distribution. For example, when you look at basic key point scenario, the objects will be at the center, and they will be pretty big in relation to other things on the image. Therefore, we do not want to predict the key points based solely on the full image, but we would like to extract crops, then use them, place them on the center of the image, and use masks to further create an image where the player will be at the center and will be the only object on which the model should concentrate. This will also enable us to avoid cases where there may be two instances per one crop predicted, where two players will be occluding each other. This can be a problematic case if you would like to extract information per crop. Now, a few words about how we have set up the pipeline in our case. For pipelines and running batch jobs in ReSpo.Vision, we have chosen Kaggle. It is very convenient because it lets you specify pipeline as a graph. There, nodes will be the basic blocks of this pipeline, but you will be able to define inputs and outputs. You also have a data catalog, which will store all the inputs and outputs, which will be specified per job. Then you can combine those nodes into pipelines, and the basic pipelines can be combined into more complicated ones. This gives you a lot of flexibility. To provide an example, a basic pipeline would be a detection pipeline, which would consist of a data loading definition, the model initialization, and the prediction node where the data loader will be combined with the model itself, and the predictions will be made. And this will be a basic pipeline for just one module. But Kaggle will let you combine those pipelines into more complicated ones. So for example, running one pipeline, you can do both video filtering, then detection of objects, players and ball, and then key points estimation on those detected players. This leaves us with the last topic, how to speed up the development process in general. First, a very important aspect is good management and debugging of the models. In order to facilitate this, it is a very good idea to create modules templates. Here we have presented a module template for a PyTorch module. It has everything you need. Model initialization part, pre-processing functions, which can be easily changed, and also prediction, where you will just call the prediction logic. Using such templates, you can facilitate model management, as many models will be able to use this same template. And this will enable easy changes of architecture and parameters of the models. Also, this way you can easily add new models to the pipeline, as the structure of the pipelines will be very similar if you keep the template consistent. This will also ensure consistency between the training and deployment. You will be sure that you have applied consistent normalization methods, and the model parameters also do not change between the two environments. It is also a very good practice to keep model configs in separate files, for example, YAML files or JSONs. Then, loading a module will consist of grabbing its parameters from this file to specify the architecture and then just loading the weights. Second aspect is how to facilitate quick and efficient experimentation. For this, I also recommend creating pipelines, creating templates. This time, pipeline templates. If it's possible, it's a good way to stick to just one framework and one library for models in your pipeline. When you create pipeline templates, you're also able to maximize code overlap between the training and deployment. You can split the pipeline into quick sections: data setup, data loaders, training, prediction, evaluation. And some of those sections can be basically copied to the deployment code, such as loaders and prediction itself. This maximizes code overlap. What you can also do is to use some additional wrapper libraries, for example, PyTorch Lightning. This will ensure a coherent structure of the pipelines that you work on. An important aspect when working in a dynamic environment where the datasets change is to ensure interchangeability of datasets. There will be many experiments which you will want to perform, and you would like to be able to easily adjust the datasets that you are using. It is also an important aspect to make the pipeline modular. Export its parts to 5 modules and then reuse them. You should also think about the data management structure, how you would like to keep your data, would you like to version it, how to structure the folders, maybe whether to keep it in a database. And another good idea is to use an experiment tracking tool, such as Neptune or MLflow. As you will for sure do a lot of different experiments, you should have a common ground for the comparison of the model performance. And a few general practices how to deliver faster results. One important aspect, especially in diverse environments, is to have well-managed datasets for training, validation, and testing. You want to train your models of different combinations of data, and especially you want to integrate new incoming data easily. You also need to have separate validation and testing datasets to correctly assess the model performance. Creating templates, both for the modules and the training, will facilitate the process of modules integration and also running different experiments. It is a very important aspect to have a separate test datasets to correctly assess the performance of the whole pipeline. This is especially important if you introduce new features or do big changes to the models. Another important aspect is to have a unified system output. Whether it will be saved in a database or in just a big data frame, it is important to be able to easily check the results and have them in one place. Then, maybe the most important part is to try to create the pipeline and the system as modular as possible. This way, you will be able to easily integrate new features and easily change the module's logic as long as the structure of the input and output is kept consistent. Thank you for your attention, and I will be glad to answer any incoming questions.
Okay, thank you, Wojciech, for your presentation. I've got some questions for you.
Okay, so I will start with saying good morning, everyone, again.
Yeah. Hi. It was a great presentation, very informative. I very much enjoyed it. Yeah. Okay, how much the analytics you provide using these deep learning based systems is better than already existing ones?
So the current approach is an approach which we call discrete two-dimensional event-based representation. Wait, I will just turn off and on my camera. It doesn't seem to help. So this discrete two-dimensional representation, which does not capture the context because it is based only on events. So you aren't able to integrate the information about what was happening in the past, how the players were positioned, and to give a context of the action, except for the action that was taken itself. So this is the first aspect. The current representation completely omits this aspect of continuity, and the players are represented basically as dots. What we want to achieve is, for one thing, to achieve a continuous representation so that we are able to integrate all this temporal information in the context. And the second important aspect is this switch from two-dimensional representation to three-dimensionality. And this is especially the case because in the current solution or in the current industry standard, the poses of the players are completely ignored. So basically, they are represented as dots, like I mentioned, and there will be no information about how this specific action was done. So we aren't able to integrate the way of how the player moves into your model or into your analytics. And this is the second aspect that we want to change.
Cool. Okay, we have a question on the chat from Camille. Can you give us any tips on winning Kaggle competitions? Because you mentioned you're a Kaggle Master, so that's an important topic for data scientists.
Sure. So how to win a Kaggle competition? Your result in the competition, to high extent, is a function of time. So basically, the more time you are able to spend, the higher the probability that you will be able to achieve a high place. And the second very important aspect is to have your pipelines and your experimentation workflow in place. So you have to be able to run a lot of experiments, you have to be able to run them in parallel, and you have to be able to easily compare and reproduce the results. So basically what you need is to have an established workflow which will enable you to easily test new ideas and also quickly find out those which are leading to improvement in the score. So basically, if you do not have this in place, you can easily drown in a lot of different combinations of experiments where you won't be able to catch those factors which really contribute to the improvement in your solution.
Yeah, you mentioned that a lot in your presentation, that you're focused on these pipelines and kind of fast deliver of every part of the project. That it comes from your previous experience on Kaggle, right?
Basically, I think I can say this. So this is a combination between my Kaggle experience and my experience in very diverse projects. So because I was able to work with different kinds of data and different kinds of projects, and some of those projects were combining a lot of models in order to deliver this solution, it needed to, so I had to, let's say, create a workflow which enabled me to easily change parts of my workflow and the pipeline so that I'm able to quickly change the parameters, quickly replace the models. And this, so this heavily influences the speed of your experimentation and therefore the delivery of the results.
Cool. And I've got also one question about the data. How do you gather the data? I guess it needs to be in high resolution. And also maybe a problem when processing. Could you elaborate on gathering data?
So do you mean what is the source of the data for us?
Yeah, also, yeah. But how do you manage with data with high resolution? Because it can be computationally expensive.
Okay, so we are able to buy matches from licensed parties. So we are buying videos of the matches. And then in terms of the high resolution, so basically most of the matches are in full HD, and some of them are in 4K. 4K processing, of course, is much more expensive, but still, if you're able to create, let's say, a good logic for the processing, then you should be able to pretty efficiently process it, because there won't be many modules which will be using the full resolution. So there aren't many models where you have to process the full 4K video. And in terms of full HD, this also isn't a very big obstacle, Because if you are able to find an efficient model architecture, or even an efficient implementation of a good model architecture, then you will be able to achieve near real-time speed on good models using Full HD or just a bit resampled resolution, like 1500 in the logger edge, let's say.
Mm-hmm. Okay. There was a question from Dominic. Do you mean tools like MLflow for the competitions? Do you use MLflow for the competitions?
We have been using Neptune, in fact, for the competitions that we were participating in. So this is a matter of choice. Basically, whichever you prefer is, so you have to experiment with both, I think, and then choose the one which suits you better. And you shouldn't only use them for the competitions, but also, of course, this is very important. So the experiment tracking is very important in competitions, like I mentioned. But it is also an immensely important part in every project where you are building diverse machine learning models. So if you want to build a model which will perform the best, you have to have this common ground for comparison. And experiment tracking tools enable you to do this easily because you are able to track all the parameters. So you can see between, so if you change sets of parameters, then you should be able to see which of them really influence the result.
Okay, cool. Okay, so Wojciech, thank you for your presentation.